So welcome to the first oral session. The first speaker is Andreas Veit. He's going to present a paper, Convolutional Networks with Adaptive Computation Graphs.
Thank you for the introduction. This is joint work with my advisor, Serge Belongie. I would like to start this talk with an example. Let's say we have a user that just took a photo of this nice dog outside and would like to understand what breed of dog this is. So now, somewhere in the background, we probably have some sort of convolutional network analyzing the photo, attempting to classify this image. So let's look at that convolutional network. We have our input image. We analyze some low-level features, maybe some colors, some edges, up to very category-specific high-level features upon which we can attempt classification. And so far, so good. So these modern ConvNets can classify thousands of different categories. So we just had the Open Images challenge the other day. It was like over 6,000 classes, I think, by the time now. So these are kind of animals, all sort of different categories, but also man-made objects. So what happens if we use this ConvNet and we perform it on this shoe? So those early layers still seem useful to us, but what about those category-specific high-level features? They don't seem particularly useful for this input image. In fact, most features in modern ConvNets are these kind of high-level features. And the reason is simply that they cannot be shared across a lot of different classes, but we would like to categorize thousands of those. So this is a problem. That means that for any image, the majority of features we're evaluating is actually not relevant to the input image. It also means that the more image categories we want to classify, the larger our networks get, and the slower or the longer it takes to classify any single image. Ideally, if after 5 layers we already know, hey, this is a shoe, we would like to jump right to a layer that can differentiate between different types of shoes. That would enable us to decompose the number of things we can recognize and how long it takes to actually recognize it. And that's exactly what we are attempting in this work. So in the remainder of this talk, I'm going to show you how to jointly learn the weights of a convolutional network, as well as how to arrange those weights adaptively for every single image. Since there's a surface resemblance, I want to quickly separate this from neural architecture search, which we will get a great talk, I think, just after this. In neural architecture search, the goal is to find a best or an optimal kind of general purpose architecture that we can apply to every single image. Our work is similar. We also try to find an optimal architecture, but we don't want to constrain the model by forcing it to using the same weights and the same architecture on every image, but we want to build a more flexible network that for each image can adaptively choose which features and which layers we actually need. So how do we achieve this? Let's go into the technical details. Here on the right-hand side is our proposed adaptive inference graph framework. On a high level, it resembles a residual network that you probably know that's in the middle. We have a sequence of residual layers, and we have skip connection bypassing each of those layers. The key difference is that for every single layer, we have a gating function that can decide on the fly whether a layer is needed or not. So that allows us to execute any subset of layers for a given image. So let's look into the details of that gating function. In particular, for this talk, I want to focus on 2 challenges. The first one is gradient propagation. So we have a discrete decision whether we use the layer or not, but the whole system we would like to train end-to-end using gradient descent. The second is mode collapse. We want to prevent those layers from reaching trivial solutions of either always activating or never activating. So the overall design of this gate comprises 2 steps. First, we are estimating the relevance of a current layer for the image, and then we decide whether we actually want to use that layer or not. So let's look into this. On the left-hand side here, you see the output of the previous layer. So that's our convolutional feature map. We don't really want to operate on the whole tensor because that's kind of expensive. Then we only look at the average values of each channel. We use an average pooling. And then we have a nonlinear function that gives us 2 scores. So one score for let's skip this layer, and one score let's execute the layer. So it gives us a rough estimate of like how relevant this layer is going to be for the current image. So now we have to make a decision. Do we use the layer or not? So the naive approach would be, let's just take the maximum. Let's look which score is higher and then decide, okay, let's execute the layer. So there's many obvious problems with this approach, but I want to focus on the problem of mode collapse for now. So just taking the maximum of 2 numbers simply does not capture the uncertainty in the model. Right? Just because one is slightly higher than the other one, we'll always choose that one. Ideally, we would more often take the layer with a higher score. So essentially, we want to look for a stochastic model that kind of chooses a layer kind of maybe proportional to a kind of some normalized relevance scores. So you can simply compute the softmax over those 2 scores and choose accordingly. So how do we do this? One standard way to introduce this kind of stochasticity is by introducing noise to the system. So we have our relevance scores, and now we simply add noise to it. Then we have noisy relevance scores, from which we then take the maximum. And it turns out there's one distribution of noise, and that's the Gumbel distribution, that has one very useful property for our approach. And this particular property is the so-called Gumbel-Max trick, and it goes back like to the 50s. The property is relatively simple. It just says that the argmax over unnormalized scores plus Gumbel noise is distributed according to softmax normalized relevance scores. So that's nice. That means we can simply take our scores, add Gumbel noise to it, and take the maximum. Then in expectation, we just execute the layer according to the normalized relevance scores. So this mostly solves our mode collapse problem. But then the argmax function is still not differentiable. For that, we build upon recent work from iClear last year that introduces the softmax relaxation to the Gumbel-Max trick. That simply says that during training, we replace the argmax by a softmax function to approximate the gradients. Then at inference time, we can simply take the argmax. We will look into the detail now. In particular, we use the so-called straight-through Gumbel. That means in the forward pass, we will actually take the argmax function, but in the backwards path, when we want to compute gradients with respect to our gating function, we will use the softmax. So how does this fit into the overall design? During training, we execute both our function as well as the gate. And we simply multiply the output of the layer by the output of the gate. So in the forward pass, that's going to be either a 0 or 1, since we use the argmax. But in the backwards pass, we replace it by the softmax, which would mean it's a score pretty close to 1 or pretty close to 0. That's training. At inference time, we don't have to compute any gradients. So we can simply execute the gate and say, this is a 0, this is a 1, and then we can decide whether to use that layer or not. One last part of technical detail is the objective function. And that's a relatively similar small change only. The first term is our normal softmax cross-entropy loss, so it's just some multi-class loss. But we also introduce a penalty on computation. And that is important to encourage the network to not simply use all layers all the time. That's what we call the target rate loss. And in particular, what we're doing is we set a certain target for every layer. Let's say every layer should be used 60% of the time. And that is a simple tool kind of to define the computational budget. And then any deviation from that is going to be penalized. And then the layer has to figure out for which subset of the data it wants to execute. OK, that's for the technical details. Let's look at the results. Let's start with the quantitative results. So this is on ImageNet. And on the x-axis here, I show the computational complexity in gigaflops. On the y-axis, we have the ImageNet top 1 classification accuracy, or I think it's the error. In blue, we can see the ResNet baselines. Right? So we have a small ResNet 50, and then we have a kind of a medium-sized ResNet 101. And then here we can see the adaptive versions of it with kind of different target rates. And what we can see is that for the small ResNet 50, by achieving actually slightly better accuracy, we can easily skip 20% of the layers in expectation. For the medium-sized ResNet 101, also by slightly improving accuracy still, we can skip over 33% of the layers. So that kind of shows like maybe the extent of which we usually tend to execute unrelated concepts. So what are those layers that we are skipping here? Like, are we always using the same ones? Are we using different ones? This is some sort of structure. So let's look at that. That's kind of a heavy slide, so let's take a moment to look at it. Again, on the left-hand side here, we have our smaller, like ResNet 50-based adaptive network. On the right-hand side is the larger one that is based on ResNet 101. Now, on the x-axis here of these plots, we show the different residual modules. And on the y-axis, we have the 1,000 classes of ImageNet. I organized them for you in high-level and medium-level categories. And there's a few observations we can make. So the target rate of both of those networks was 60%. First of all, there seem to be a few key layers that are always executed. That is, the downsampling layers and the last layers. So although our incentive was just use them 60% of the time, they seem to be so crucial to the performance that they're always needed. Further, we can see a clear distinction between those layers activated for animal classes, that's the one on the bottom, and those for man-made objects, that's the one on the top. We can even see differences between some mid-level categories, such as, I guess, birds and dogs, or other type of animals. That means that the network discovered by itself some part of the label hierarchy, although nothing in the objective function ever told it to separate some sort of parameters or computation. That kind of behavior emerges naturally when constraining the computation. Then there's one more aspect that's important for this new framework. Now, since we don't have the same network anymore for every single image, from a practical perspective, the inference time is also different for every image. And it seems to follow this kind of normal-like distribution. I've also pointed out here two different subsets of categories. And we can see that for birds, I guess one residual block less is needed than for consumer goods. But now let's try to get an intuition for what are those images that need a lot of computation, or what are those images that only need a very few layers. So let's look at these examples. So here on the top row, I've shown the examples from these mid-level categories that need the least computation. And you can see these are very iconic images, right? We have an iconic bird or dogs here. And on the lower row are those that need the most computation. So that's where the model has a lot of uncertainty. Those are occluded objects, very small objects, or just unusually looking objects. So maybe one theory could be that just images of birds seem to be maybe more iconic in general over ImageNet, which means why they need less computation over our validation set. All right, the time is running short, so let's come to the conclusions. So if there's one thing I want, I guess, everyone here to take away is that convolutional networks don't need a fixed feed-forward structure. Further, we've proposed a framework where we can adaptively generate inference graphs that both improves the efficiency as well as the classification quality of the ConvNet. With that, I want to thank you for the attention. There might be time for a question or two now. Otherwise, find me at the poster or find my contact online.
We do have some time for questions, so is there any?
Hi.
Oh, there.
Have you looked at the connections to neuroscience with the brain taking different lengths of time to execute inference in the visual cortex?
So we took it as some sort of inspiration, but we are very careful in not taking too many parallels, since I don't have that background in neuroscience. But if you have, it would be very interesting to chat to kind of see what parallels there would be. Yeah, you can just come to the mic, I guess.
Thanks, first of all. In many applications, especially inference applications, you always have to be prepared for the worst case, where you have, an image full of very complex things, and especially if you sell it to a consumer who expects a very high reliability, it's hard to tell them, hey, by the way, when there's a lot of stuff going on in the video feed, then we have to use more layers, and suddenly the frame rate drops. What's your comment on that?
Right, and that's a very good question. That's exactly what I wanted to get at with that one slide. Is of course you have an upper bound, right? So you always have an upper bound of how many layers you have, right? That's the maximum number of inference time. So I would more think of it like you have the potential of being faster, right? But of course you have to figure out for your own application of how you want to design that variable inference time. Yes?
Is there any connection between your work and some model compression works, existing works on model compression? So you have a very large model, but you try to remove some layers, try to remove some, you try to make work on mobile devices, say ResNet 101, where you have a smaller model which can be used in the mobile devices. That's called model compression. Is there any connection between your work and those existing works?
I mean, these two concepts are, I guess, somewhat orthogonal in the sense that we don't try to make the model smaller, right? That's kind of, you can also attempt to do that, but we are trying to separate the parameters in the model so that we can on the fly choose which parameters we need. I guess if you can safely assume that all images that you're taking in the model are in a shopping scenario, right? Then you could actually use that technique for model compression, but then of course you would use generalization to other kind of scenarios.
Okay, sorry, we're running out of time, so let's thank the speaker again.